Okay, today's topics are going to be regarding reactions in aqueous solution, chapter 7 of our text. These barrels in the picture are suggesting some substances that would be hazardous wastes, and there is such a thing as a concept called green chemistry that is mentioned in the text at the end that talks about strategies to reduce the amounts of things that are toxic and hard to dispose of. But we have to understand something about reactions in aqueous solution to do that. All right, for this chapter, we have a set of learning objectives, and let's see which ones we should cover to begin with, if I can get the slide to advance. So, chapter 7 objectives that will be discussed first in this particular recording will be how we describe things as electrolytes or non-electrolytes. We will proceed to topic number 1 after that. So what in the world is an electrolyte? It kind of has in its name what it actually is. So it's a substance when you dissolve it in water that has a solution that can conduct electricity. There are also substances which are therefore not going to do the same, so we call them non-electrolytes. They do not conduct electricity. And so here's an example of what you would see if you had the electrodes in a solution that's a non-electrolyte. The bulb is dim. There is such a thing as a weak electrolyte where it conducts electricity but not terribly well. And there are strong electrolytes which conduct electricity really well. So it has something to do with what's dissolved in water for those two substances that qualify as electrolytes. One is stronger than the other. So it comes down to this notion that electrolytes are substances that produce conducting solutions of ions. And that's one key thing that we can't overlook. You have to have ions present. So for example, if you put sodium chloride in water, the solid will cause the sodium chloride to separate into separate ions of sodium and chloride. And the diagram at the right suggests to us how the circuit is completed, because the positive electrode attracts anions, and the negative electrode attracts the cations, and it completes the circuit. So the movement of charged particles is what allows the circuit to be complete and allows the light bulb to glow. If, on the other hand, you have a non-electrolyte, you have electrodes of the negative charge and a positive charge, and you stick something in there and it doesn't produce any glowing of the bulb because there are no ions. Non-electrolytes don't have ions, and we have to get ourselves straight from the outset to realize that only ionic compounds, in a very broad sense, but generally we think mostly of ionic compounds, are going to be electrolytes. Sucrose is sugar, table sugar, and it is a molecular compound. And so it is seriously not containing any ions. When you put it in water, it dissolves in water just fine. You've seen sugar dissolved in water. But it does not have any ions to conduct electricity. So there is no attraction of the particles for either of the electrodes, and the bulb remains dim, dark. So putting the two side by side, you have to recognize that there's cations and anions being attracted to electrodes for an electrolyte, and it makes the light bulb glow. On the other side, there are no moving charged particles when it is a non-electrolyte, such as sucrose. Sucrose is just one of several examples that we'll come across that are molecular compounds. All right, now, there are strong electrolytes and weak electrolytes. How do we know what's what with the difference between them? The compounds that dissociate to a large extent, in most cases a very large extent, when we call them strong electrolytes, when we dissolve them in water. So HCl, hydrochloric acid, is one example of something that's dissolved in water, which completely dissociates into its separated ions when you put it in water, or potassium chloride, another chloride compound, which as a solid can be stirred into water, and you get separated potassium and chloride ions. Weak electrolytes dissociate to a small extent into ions when dissolved into water. And the example shown here is acetic acid. Acetic acid, like many acids, is actually a molecular compound, but it's a molecular acid. And these things will ionize, some of them, to a small extent, but providing a few ions, but not necessarily to the large extent as evidenced from strong electrolytes. So there will be certain compounds you have to just become familiar with gradually that are weak electrolytes and some that are strong. And we will gradually have ways to recognize them. So when electricity is conducted in solution, what's happening? You've got cations and anions, and the strong electrolyte, essentially 100% dissociation into those cations and anions. And so for sodium chloride, you get sodium ions and chloride ions, many, many mobile charged particles, and that's what conducts electricity. So mobile charged particles allows for a current to be conducted in that solution. A weak electrolyte is not completely dissociated, and for example, that's acetic acid again. You have a back and forth process that's described as an equilibrium. We'll talk about equilibrium elsewhere, but there's some forward and some reverse reaction taking place, and you get some of the acetate ions and some of the dissociated, whoops, I spelled it wrong, the acetate ions and the dissociated protons from the acetic acid. Acetate is the name of the ion. We sometimes forget that ion. And so only to a partial extent does that occur in a weak electrolyte such as acetic acid. So they don't have very many charged particles when it is a weak electrolyte. I want to add the name here too, so I want you to recognize it sooner or later. Acetic acid is present in vinegar. It's not a very uncommon compound. So if you're looking at 1/10 molar solutions of these two substances, which easily can be prepared, they're soluble in water, but the potassium chloride compound mixture solution would have nearly 90%, essentially 90% of its ions dissociated, and so that large forward arrow suggests that it's greatly dissociated, and we call it a strong electrolyte. The other one is the acetic acid again, which is mostly not dissociated. In fact, 99% of it stays intact as the acetic acid form. A very small portion of it dissociates to make the acetate ion and the hydrogen ion. So very weak when the reaction is primarily when there's very little dissociation, like 1% versus 98. Okay, then there are ways of classifying compounds that help us to understand when things are strong and weak in non-electrolytes. To begin with, there is a set of strong acids. There are only 6. There is the only 6 that you will ever be asked to know that I can imagine. If anybody has more on their list, I don't know where they got them. And the first 3 are from the halogen family, so hydrochloric, hydrobromic, and hydroiodic. Notice that it doesn't include fluoride, in that list of acids. It instead is a weak electrolyte over here. But these are things that will dissociate nearly 100%. That's why they're listed as strong electrolytes. So 100% dissociated into ions. And there are a few other things on this list that you should know about. We will get to them as we go. So know those strong acids. In addition to the ones from the halogen family, there's perchloric acid, the one below there, that's not as familiar to us. This is nitric acid. We'll talk about naming the acids later in the chapter. And this one is sulfuric. So these 6 are ones that you should know. Put them on a list someplace and pay attention to them. Okay, so those are strong electrolytes. What other things are strong electrolytes? Well, the bottom of that list has some other compounds on that column, and those are ionic compounds. There's a lot of ionic compounds that are going to be strong electrolytes. We will, with time, elaborate on which compounds are soluble in water, but they're mostly going to be a lot of ionic compounds that fit that category. Things with potassium and sodium are very, very commonly soluble, and we'll learn about that with some rules in about section 4. The next group of compounds then is the weak electrolytes. These things are going to be weak acids. They're molecular acids again, and they have only partial dissociation to make ions, so they're not very many ions present. Partial dissociation or incomplete, and few ions present. Partial or very limited. dissociation, not nearly as much. The last group of compounds then are the non-electrolytes. These things do not have ions, and they're going to be molecular compounds overall. Water actually is included in that list. We kind of forget that water is actually a molecular compound. Alcohols fit that category, sugars fit that category, and in a general sense, organic compounds, compounds of carbon, are going to be non-electrolytes. They do not contain ions. The only molecular compounds that contain ions are the weak acids from that weak electrolytes column. Okay, good things to be aware of. So if you have two kinds of conductors, they're either weak conductors or strong conductor, good conductors or poor conductors. So a weak acid is a lousy conductor, and a strong acid is a really good conductor. Maybe sometimes cartoons help us. We like a little humor. All right, but visual representations of these things are always helpful, and they may not be your favorite thing, but let's try them. This example of ions of things dissolved in water. The water molecules aren't included because it just makes for messy diagrams. And we have to decide which is the strong electrolyte and which is the weakest. And so we apparently have anions and cations. The blue and yellow and red must be the different kinds. And in the first box, what do you see? There are 1, 2, 3 separated ions, and so 3 ions and 4 of the compound or molecule, if you will, but let's just call it a compound because we can't verify that they're actually ions. Well, probably it is. And then the second box, they're all separated, nothing's together, all separate. And then in the last box, we see 1, 2, 3, 4, 5, 6, 7, 8 are separated, and 2 compounds are intact. So 2 are intact. So which one is the strongest electrolyte and which is the weakest? So the strong electrolyte is the one that dissociates the most, and I hope you figured it out by now, would be example number 2. And the one that dissociates the least would be the weakest electrolyte, and that would be example number 1. All right, example number 3 is somewhere in between. Now, which of these reaction systems would conduct electricity? We have to look at these things, or which one would do it well. So we have an example of putting potassium bromide with water to make potassium ions. Oh, that's a typographical error, sorry. That should be a negative ion, huh? And each of those are incorrect for that, but I'll fix them. And you get potassium and bromide ions, and water is still there. And the second example is hydrogen fluoride. We'll name that later, but it's a cousin to HCl. When you put it in water, you get some hydrogen ions and fluoride ions, but you also have still some HF and still some water. So which ones would conduct electricity? Well, you have to have mobile charged particles in order for electricity to be conducted. And each of these has some ions present. So it would be both A and B. It turns out that B is a weaker electrolyte, but at least there are some ions. We're not going to qualify which one is which in this particular case. Now, when we're talking about dissociation of ionic compounds in solution, it's helpful to think about an equation to represent the dissociation process. So you take something like sodium sulfate, you add water to it, and you have sodium ions that are now aqueous. That means each ion is surrounded by water. And we'll list it that way in the reaction expressions by water molecules on all sides. And the same thing will be true of the sulfate anions. And so those are both aqueous. And that's what happens to sodium sulfate when you put it in water. But notice, because of the coefficient or the subscripts in the compound formula, there will be 2 sodium ions for each sulfate ion that is produced when the compound dissociates, for a total of 3 ions for 1 formula unit. Sometimes we don't think about that, but it makes sense when you remember the names and identities or formulas for ions. The second example is simpler because it doesn't have any polyatomic ions in it, but iron 3 bromide can be dissolved in water to make iron 3 ions, again aqueous, and 3 bromide ions. So again, because of the subscript after the bromine in the formula, you can recognize that there should be 3 separated bromide ions when they're dissolved in water. So there's a total of 4 ions per formula unit for that compound. So every compound that's ionic will have a different possible number of ions when you dissolve them in water. We'll take that one step further now to think about how these are used in a calculation. So if you put that sodium sulfate in water and get sodium ions and sulfate ions, what would be the molar concentration of the sodium ions if the concentration of the sodium sulfate that you dumped in is 0.5 moles per liter? Well, there are two moles of sodium ions per mole of sodium sulfate. And that's part of what we have to understand here. And I'm doing this in the order I might not have chosen. But if you have 0.5 moles of sodium sulfate, whoops, put the 2 in, per liter of solution, the moles of sodium sulfate cancel, and now you actually can calculate the concentration of the sodium ions would be 1.0 molarity for sodium ions. Fair enough. If we wanted to do the same thing for sulfate ions, well, again, we have 0.5 moles of the sodium sulfate per liter. And in this case, it's very simple because there's just one sulfate ion, or sorry, 1 mole of sulfate ions. Ah, come on, tool. Maybe I can fix that another way, sorry. 1 mole of sulfate ions per mole of sodium sulfate. And so it's a 1-to-1 ratio, no big deal. You have 0.5 molar sulfate ions in this solution. Okay. Oops, sorry about the extra line. Now, the other way these questions will be posed then is to think about the total number of ions in the solution. So for the total molar concentration of ions, we simply add those up, and the answer is 1.5 molarity is the concentration of ions. You could get that also by saying 0.5 moles of sodium sulfate per liter, and there's going to be 3 moles of ions per mole of sodium sulfate. And that comes out to give you the same actual thing. No big deal. All right, that was still fine. Let's just do one more for comparison. Let's look at the other example that I had on the previous slide with the iron 3 bromide. So if you have the iron 3 bromide, let's just try that one and see if we make any sense of that. So the iron ions in the iron 3 bromide, if you have 0.5 moles of iron 3 bromide per liter, then you have, in this case, well, I guess it's just 1. So that was easy. 1 mole of iron ions per 1 mole of iron 3 bromide. And that means the concentration is 0.5 molar of iron ions. Now, do the bromide also. So the bromide ions, if we said we had 0.5 molarity of, or molar solution of iron 3 bromide. Either way of saying those is correct. And you could have written it, I could have written it as moles per liter, and I just wrote it as capital M. But we get the right idea here. I should have written it out. Maybe that'd be smarter. Let's write it out just to make you feel more clear. So 1/2 mole of iron 3 bromide, I forgot the 3 up there, per liter, and there will be 3 moles of bromide ions per mole of iron 3 bromide, which isn't hard to do. The iron 3 bromide cancels, and the concentration of the ions, the bromide ions, is 1.5 molarity. So the total molar concentration of ions then would be the sum of the 2, or 2.0 molar ions. But you could do it the same way as I did on the previous example. 0.5 moles of iron 3 bromide per liter, and there are 4 moles of ions total per mole of iron 3 bromide. You have to remember what your polyatomic ions look like, or you'll get fooled. In this case, there weren't any. In the other example was sulfate. The sulfate is sulfur and 4 oxygens without any separation of those. All right, this is my initial conversation then about electrolytes in aqueous solution and how they dissociate. I hope you find this helpful. Good luck on your homework. Ask more questions as needed, and I'll see you in class.